Section 4.4, Logarithmic Function. So to start with, we got to recall exponents. So remember that the exponential function f of x is equal to a to the x is 1 to 1, and therefore you can have an inverse for it. Now the question then becomes, what is that inverse? And so how do we find inverses? Well, we exchange x and y, and then we solve for y. So if we want to find the inverse, let's run through that process again. If we have f of x is equal to a to the x, then we take f of x, we replace it with y, and then we exchange the x's and the y's. Well, now we have x is equal to a to the y. So then we would like to solve for y. But the deal is that y is really the power that a must be raised to in order to get x. And so this is actually the inverse of the exponential. But we're going to give it some notation. So the notation that we're going to give for the inverse of the exponential, that is, the power that a must be raised to in order to get x, we're going to call this a logarithm. And so that's exactly what a logarithm function is. Y equals log base a of x. That's how we read it. But once again, it is exactly what we just stated. That is, y is equal to the power that a must be raised to get x. And so when you're looking at log base a of x, that's the question. A raised to what power y gives us x? So if you're lost at any point, you can just rewrite them. And so understand that a to the y is equal to x is the same statement as y is equal to log base a of x. Once again, y is the power a must be raised to get x. Now there's some few notations that we need to address. If no base is given, then we're going to assume that a is 10. And we're going to call this the common log. And so if you ever see log of x, if you're looking at your calculator, log of x is log base 10. Now, a couple properties that pop out. Because we know that a raised to the 0 power is equal to 1, well then what happens is if I ever ask the question, what is log base a of 1, you're really asking the question, a raised to what power equals 1, and of course the answer is 0. Additionally, we have a to the first is always equal to a, which means that if I have log base a of a, you're going to get 1. Now let's phrase this question the correct way. A raised to what power equals a? We're also going to have a natural logarithm, and the natural logarithm is going to be with a base of e. And so remember that e is a transcendental number, and so log base e of x is the exact same thing as the natural log of x. But in general, we'll never write log base e, we'll always write ln. And of course, because e to the 0 power is 1, that means that natural log of 1 is equal to 0 because log base e raised to what power equals 1? Well, the answer is 0. E to the 0 power equals 1. And then of course, because e to the first is equal to e, then the natural log of e will also have to be 1, but let's phrase the question correctly. The base e raised to what power gives us e? And the answer is 1. And these are just some facts that are very useful if we need to evaluate logarithms, which we will be. So first we want to change the exponential statements that are given to an equivalent statement using a logarithm. So this is just using that definition of a logarithm. We're just going to swap it to the logarithm statement. So what is our definition? That is y is equal to log base a of x is the exact same thing as saying a to the y power is equal to x. So here I have my base 2. And so the equivalent statement of this would be log base 2 of 8 is equal to 3. 2 raised to what power gives us 8? 2 cubed gives us 8. Here if I have 7 to the first is equal to 7, well, to write this logarithmic statement equivalent, that is log base, this is my base, 7, of, what's on the other side, of 7 is equal to, well, of course it's 1, because 7 raised to what power equals 7. E to the 5th is equal to m. An equivalent logarithm statement would be log base e, but the moment that I have log base e, I'm not going to write that, I'm going to write natural log. So the natural log of m is equal to 5. E raised to what power will give us m? Now we're going to write the logarithmic statement as an exponent statement. So, same definition we just used. We have this base 2 cubed is equal to 8. That's how we write this. The base, the power is equal. Here we have a base of 1/2. So this is 1/2 raised to the negative 5th power is equal to 32. And if you were to confirm, that's true. Log base 9 of 3 is equal to 1/2. That's the same thing as saying 9 raised to the 1/2 power is equal to 3. Well, of course, the square root of 9 is 3. Now we just want to evaluate some of these logarithms. So if I have log base 4 of 16, well, you could rewrite this in a different way. You could say 4 raised to what power equals 16. And so my y is what we're trying to find. 4 raised to what power is equal to 16? But the answer is 2. 4 squared is 16. Here, if I have log of 1 over 100, remember that here the base is 10. And so if we don't know what to say, or rewrite it using our definition, the base is 10. 10 raised to what power y is equal to 1 over 100. Well, at this point, I'm thinking 1 over 100 is the same thing as 1 over 10 squared. And then if I need it to be a power on top, that's the same thing as 10 to the negative 2nd power. And so now I know that y, negative 2. 10 raised to the negative 2nd power will give me 1 over 100. Here we have the natural log of the cube root of e. Well, what is this? This is the same thing as saying ln is the same thing as base e. E raised to the y power is going to be equal to the cube root of e. Well, how can we write cube root as a power? Well, that's the same thing as e raised to the 1/3 power, which now tells me that y here is a third. E raised to what power gives us the cube root of e. Often enough, we need to find the exact values of logarithms, and so we'll use properties of logarithms to do that. We haven't talked about many properties, but we'll talk about more properties in the next section. But if you're just trying to get an approximate value, then it's possible to use your calculator to find these values. But they will be approximate values, not always exact. Now, if you're looking for natural logarithms, use the ln button. If you have other logs that aren't common, because our calculators only have 2 logs on them, log base 10 and ln. And so if you're trying to calculate those other ones, then you will need to use the change of base formula. And so the deal is the change of base formula goes like this. Given any logarithm, log base b of m, then you can rewrite this as log base any base you choose of m divided by log any of that matching base, base b. Well, how does this equate for us? Well, what this really says is that if you're trying to calculate things using a calculator, log base b of m can be calculated in one of 2 ways. Well, let's fix one of the bases on our calculator. Well, let's do log base e. So that's the same thing as saying that's the natural log of m divided by the natural log of b. And so we can calculate any logarithm that we so desire, find an approximation using ln of the input of that logarithm divided by ln of the original base. Equivalently, you could use log base 10, that is, log of m divided by log of b. And so either one of these is a perfectly good choice if you're trying to find an approximate value using your calculator. But let's just try some of these approximate values. ln of 18/5. Notice that 18/5 is the thing that's going into the natural log, so make sure you put a parentheses around it. Then it's just a calculator value. And we are rounding our answers to 3 decimal places. And so the ln of 18/5 is approximately 1.281, 3 decimal places. Similarly, if I'm trying to find ln of 93/7 over 0.02, that's going to be the same thing as 2.587 divided by 0.02, which is then, of course, going to be 129.334. Then log base 8 of 5, this one we're going to have to use a change of base. Now it's up to you if you use natural log or log base 10. Either one of these is perfectly fine. I'm just going to use natural log for my preference, but it doesn't matter. Well, because of the change of base formula, that means that log base 8 of 5 is exactly the same thing as the natural log of 5 divided by the natural log of the original base 8. Now one more time, you could also use the common log, that's log base 10 of 5 divided by log base 10 of 8. And I would say check both of these to verify to yourself that it doesn't matter which one you use, because both of them are going to give us an approximate value. At this point, I'm just going to find natural log of 5 divided by natural log of 8. And I get that this is approximately 0.774. If we're trying to solve logarithmic equations, we can just rewrite the equation in exponential form and then use the properties of exponents to solve these things. And so if I want to solve the equation, log base 2 of 2x plus 1 is equal to 3, I can rewrite it using its equivalent definition. Its equivalent definition is 2, that's the base, raised to the third power is equal to 2x plus 1. Then we can just solve this equation. 2 cubed is 8. Equals to 2x plus 1 minus 1 minus 1. 7 is equal to 2x. Divide by 2, divide by 2. X is equal to 7/2. Now technically we should be making sure that we know that the domain of logarithms is just from 0 to infinity exclusive. We don't include the 0. And so as long as we can plug this back in and the input for any logarithm is a positive number, we're fine. 7/2 times 2 is positive, plus 1 stays positive. Here, for the next one, I have log base 3 of 243 is equal to 2x plus 1. So, using the equivalent definition, that is the base 3 raised to the 2x plus 1 power is equal to 243. Well, at this point, it could be a little daunting. But I'm going to take a wild guess and I'm going to assume that I need to write 243 with a base of 3. And then we can notice that 243 is really 3 to the 5th power. Well, that means that because I have 3 to the 2x plus 1 is equal to 3 to the 5th, because my bases match and I just have a single one on each side, then I can just set the exponents equal to each other. 2x plus 1 is equal to 5, minus 1 minus 1, 2x is equal to 4, divide by 2, divide by 2, x is equal to 2. But look at here, there's no issues with the domain, so we're perfectly fine. If I have log base 2 of 8 to the x is equal to negative 3, that's the same thing as saying 2 raised to the negative third power is equal to 8 raised to the x power. Well, then I could rewrite 8 as a power of 2, so 2 to the negative third, we know that 8 is really 2 cubed, so this is the same thing as 2 cubed raised to the x power. Then via power rules gives me 2 to the negative third is equal to 2 to the 3 times x. Then I have 2 to the negative third is equal to 2 to the 3x. That's then I can set the exponents equal to each other. Negative 3 is equal to 3x. Divide by 3, divide by 3. X is equal to negative 1. We should plug that value back into our logarithm just to make sure that we don't get a negative number logarithm, but 8 to the negative first power is really 1 over 8, and so we're perfectly fine. Here I have the natural log of e to the x is equal to 5. That's the same thing as saying, well, the base for ln is e. E to the 5th power is equal to e to the x. So, set the exponents equal because now we have matching bases. 5 is equal to x, and we're done. Log base 4 of x is equal to 3. That's the same thing as 4 raised to the 3rd power is equal to x. This one's just a calculation. 4 cubed is 64. And it's positive, so we're perfectly fine. Here we have 5 raised to the x power is equal to 625. And of course, that is 625 is the same thing as 5 to the 4th, and then setting our exponents equal, x is equal to 4. Now some common characteristics of log base a of x and the natural log of x, so really any base that we so desire. They are continuous and one-to-one. Their domain is from 0 to infinity, but we don't include the 0. Now that's before any transformations. So in general, if you have a logarithm, you cannot put a negative number or a 0 into it. The range of logarithms is all real numbers. Vertical asymptotes occur at x equals 0 unless there's a horizontal translation. The x-intercept is going to be the value 1, 0. And if we're considering the graph of y equals log base a of x, there's two situations that occur. And if you want, remember that we know that a logarithm is really the inverse of the exponential. And so since they're inverses of each other, this blue one is my exponential graph, where a is a number between 0 and 1, and we know that that is a decreasing function. Then if we use the line y equals x, we know that inverses have to reflect across that line. And so reflect the blue line across this y equals x, and we will get this pink or red line. So now I see that this is what the logarithm looks like when my base is a number between 0 and 1. It's actually going to be a decreasing function with vertical asymptote at x equals 0, and it will just decrease as we move to the right. Then, if the base of our logarithm is bigger than 1, well, what's that going to look like? Well, first, let's think about the exponential function. The exponential function is going to be an increasing function. Then, when we reflect it over the line y equals x, we get the logarithm function that is also an increasing function, and we have the vertical asymptote at x equals 0. So now let's discuss some graphs. And we know that transformations work exactly the way as all our other transformations do. And so if I consider this f of x is equal to the natural log of x minus 3, notice that we do have a parent function. That parent function is the ln of x, or log base e of x, which will look like this because e is bigger than 1. Well, at that point, we have one transformation that's inside, so it affects horizontal stuff. This specifically goes right 3. Now, because this thing shifted right 3, remember that we do have a horizontal asymptote for the unchanged parent function at x equals 0. But now that we shifted it to the right 3, we'd get a new vertical asymptote at x equals positive 3. Now, this is helpful because now, since we have no horizontal reflection, we know that the domain is going to go from positive 3 up to infinity, but do not include that 3 because, of course, it will not touch or cross that asymptote. Then for the range, we know that the range is going to be all real numbers. And then let's graph it. So if we're going to graph it, I'm going to graph this one in red. We have that vertical asymptote at x equals 3. But then if I want to find other ordered pairs to make this graph look much better, it's probably going to be best if we find the inverse. And so that's why I've got this on here. So if we want to find the inverse, remember that first off, I just rewrite f of x as y. And then to find the inverse, I exchange the x's and y's and solve for y. So that's going to be x is equal to the natural log of y minus 3. Well, then using the definition of what a logarithm is, this says the same thing as e raised to the x power is equal to y minus 3. Then if I'm solving for y, add 3, I get that y is equal to e to the x plus 3. And so that's my inverse. My inverse function is e to the x plus 3. If you wanted, you could, of course, start plugging in values for this inverse function, such as 0, or 1, or 2, and you could find approximate values and plot those ordered pairs. I know that the domain of all exponential functions is all real numbers, and so nothing's really changing here, other than the fact that, of course, we're getting that from the range of the previous. And then the range is going to be exactly the domain from our initial function. That's going to be from 3 to infinity. And then if we want to graph this, remember that we do have this horizontal asymptote at positive 3 now. And I get this fixed point here. And I could find another one. The next one should be about there. And so I claim that's what this looks like. Well, now that I've got the inverse function, I can go back and I can reflect that across the line y equals x to get an accurate representation. And so notice that this one, mirrored across the line y equals x, will look about like this. Now, I know that it appears that it's approaching the opposing graphs or the inverse function's other asymptote. It's approaching it, but they're unrelated. It's going to cross it at some point. Don't even worry about that. It just happens to do it very quickly here, so it's off the page when it occurs. Let's try another one. So looking at this one, let's first find the transformations. Well, before we find the transformations, let's recognize that our parent function is the log base 10 function. That is, when we don't write a base, it is log base 10. And so log base 10 of x is going to look like this, more or less. Then what is our transformation? Notice we have two transformations. This goes left 2 and down 4. So left 2 and down 4. Since it goes left 2, we now know our vertical asymptote is x is equal to negative 2, which then tells us that we know the domain. The domain is going to go from negative 2 up to infinity, and our range is going to be, of course, all real numbers. Well, then if I want to graph this thing, if we're just concerned about a quick sketch, well, we know that we have this vertical asymptote at x equals negative 2. The original point that would originally have been on the parent function at 1, 0, well, that one is now shifted left 2 and down 4. So left 2, down 4. So we know that we have this point right here. And then if we wanted to find more points, we could. It might actually be easier to work with the inverse. But I claim that our function should look about like this. Now if we want to find f inverse, remember that f inverse is going to be gotten by replacing f of x with y and then swapping the x and y values. That gives us x is equal to log base 10 of y plus 2 minus 4. Then we can solve for y. So add 4, x plus 4 is equal to log base 10 of y plus 2. Then we can use the formal definition of a logarithm, that is, the base 10 raised to the x plus 4 power is equal to y plus 2. Well, then we finish solving for y, minus 2 minus 2. Then I get that y is equal to 10 to the x plus 4 minus 2, and that's my inverse function, 10 raised to the x plus 4 power minus 2. Then if we want to know the domain and range, of course the domain and range can be gotten directly from the original function just by swapping them around. That is, the domain of the original function was negative 2 to infinity, therefore that will be the range for its inverse. And then the range was from negative infinity to infinity, and so the domain of the inverse function is going to be all real numbers. Then if we want to graph this exponential function, remember that it has a horizontal asymptote is shifted down to negative 2, and so we get this. And then we had that original point that would have been at 1, 0, but is now shifted down 2 and left 4. And so if I were to graph this exponential function, it will look about like this. Then, of course, you can notice that if we were to plot the line y equals x, notice that the reflection across this line, you get the blue and the red graphs, respectively, because they are inverses of each other. And so you could use that line as a reference, y equals x, being where you mirror these two graphs.